Hello everyone, my name is Maria and today I'm going to talk about generating unlimited resolution sonar images using R2D2-GANs. Underwater the visibility is quite poor, as in the picture on the left, so people usually use sonars. These are these bullet-shaped vehicles as in video on the right. They fly underwater and record the reflected sound signal, which later on turns into the images looking a little bit like that. On the left hand side you can see the aerial view of several underwater missions as recorded by sonars, and on the right hand side you see what teleoperators see on their screens. Extremely long, high resolution imagery. Why simulate? So sonar data are very expensive because of the equipment required to collect them, and hence there is lots of commercial sensitivity issues involved, so companies are not capable of sharing them amongst themselves. So simulated data might be a good idea. So there are two main potential uses that we are going to discuss, which is visual simulation for training teleoperators and data augmentation for training autonomous target recognition systems. So there are methods that are well known for their image generation and translation called Generative Adversarial Networks. I'm going to talk a little bit about how they work. So they typically feature two networks. One is generator, one is discriminator. Generator inputs noise and outputs hopefully realistic looking data. And discriminator takes these generated images along with real images and tries to distinguish one from the other. So the target of generator is to fool discriminator, and target of discriminator is not to be fooled. As these two usually train together, they usually improve via competition. So we came up with a method that would be capable of generating extremely high resolution images by doing that sequentially, tile by tile. If you look at the left side, that's the training algorithm. So first, the green cycle of the generation. So the generator produces something realistically looking using C1 and C2 snippets that come from above and to the side of the image. And then discriminator uses exactly the same input to try to distinguish whether it's real or fake. That's discriminator 1. Discriminator 2 looks at the bigger picture to see whether the picture makes sense as a whole after all of these little tiles get together. Then at the test time, we completely discard discriminators. We use only generator. So again, as I said, it goes left to right, top to the bottom. We always use C1 and C2, so the pixels from the top and from the side, to make sure the consistency and continuity of the image. You can see the loss function here, and although it looks very complicated, I can tell you that it's literally just the normal GAN function, except for it accommodates for two discriminators here, so it basically finds the average between their losses for backpropagation. So here are the visual results. This is for EdgeTech. That's the sonar that's 4,620 pixels across the track in resolution. You can see how good are the images. So on the left-hand side, it's real, and on the right-hand side, it's fake. It's simulated by R2D2. This little snippet at the top left, generated by Markov conditional pics-to-pics, previous state of art. We show these images to people who work with them on a daily basis, teleoperators. We showed one image at a time and asked to label it as either as real or as fake. As you see, the results come as follows. Pics-to-pics for a baseline, R2D2 unnormalized and R2D2 normalized. It's nothing much, it's just normalized across the columns. First column is fake labeled as real, which means a simulated image labeled as real. And as you see, the last entry, so our method, actually wins. It shows 78% realism. That's compared to 90% of real images actually being labeled as real, which is pretty good. Labeling accuracy is close to 50, which is close to random chance for two-class problem. Two-class problem is real or fake. So it's a pretty good result, much better than any of the competitors. People take longer to try to inspect these images. It's also applicable for autonomous target recognition, while bootstrapping the systems. So basically generate the data to train ATRs. In this case, it's simple ResNet. And as you see, here we compared training on different sorts of images and then testing on real. We compared just random noise background, sonar sim, flat and rippled, that's a different kind of sonar images, and then we compared our R2D2-GAN as training data for later on testing on real, and as you see, the best results come again from our method. So that's it. If any questions, do let me know on this email on the slide, and thanks for watching.